the last section for Unit 4 is on molecular formulas, which you're going to find is actually pretty similar to Section 3 with empirical formulas with just one extra step. So some of this is going to be a little bit of review from the previous section. Okay, so with empirical formulas, I told you that it does not always indicate what the actual compound is. It was just simply, right, the lowest whole number ratio. Well, with molecular formulas, here's your definition. A molecular formula is the chemical formula which specifies the actual number of atoms of each element in one molecule or formula unit of the substance. So for instance, we could find that the empirical formula of a compound is, say, HO, where it's one hydrogen and one oxygen. But the actual formula might end up being H2O2. Okay, but when we find it, originally it would look like this, because that's the simplest, right, the lowest whole number ratio would look like this, 1 to 1. But it might actually be 2 to 2. So the molecular formula is going to be what it actually is. So here's an example problem. Determine the molecular formula of butane given that its molar mass is 58.14 grams per mole and it is 82.6% carbon and 17.4% hydrogen by mass. So it's actually going to be solved pretty much the same way as empirical formulas with one step at the end. Right, so our solution is going to begin by finding the empirical formula of butane. Right, that's going to be assume 100 grams of butane and then convert all of our percentages into grams, grams into moles, find the smallest mole ratios, okay, and then finally use the molar mass of the compound to find the molecular formula. So this is the one step that's going to be new down here, okay, compared to what you did before. So this part isn't any bit new. We're going to turn the percentages into grams, divide by the molar mass, so 82.6 grams of carbon divided by 12.01 gives us 6.88 moles of carbon, 17.4 grams of hydrogen divided by 1.01 grams per mole gives us 17.23 moles of hydrogen. Divide each by the smallest number there, okay, so that would give us 1 mole of carbon. We get this interesting 2.50 moles of hydrogen, which makes it look as if our formula would be something like CH2.5, but since for an empirical formula, it has to be, right, the lowest whole number ratio. Right? We've got to figure that out. So we can't leave it like this. And the next slide is going to talk about what we do. So the empirical formula can't be this CH2.5. Right? It's got to be whole numbers. Well, in order to fix that, what I need to do is get rid of this half of a number here. It's really like saying I have C1H5 over 2, right? 5 halves, 2.5. Well, if I wanted all of those to be whole numbers, what I would do is I would just take the whole thing, and to get rid of this denominator right here that's a 2, I would just multiply the whole thing times 2. Oops, what happened with my Apple Pencil there? Times 2, okay, and that would give us C2H5. Now this would be your your empirical formula, right? That's our empirical formula. The simplest whole number ratio, 2 to 5, 2 carbons for every 5 hydrogens. So that's actually what the empirical formula is, not this right here. And you're actually going to see some on your homework assignment today that's going to give you the same sort of thing. So if you get kind of like a ratio like 2.50, you know that's a half. Or if you get something like 0.33, you know that's a third. Or 0.67, you know that's 2/3, right? Or 0.75, you know that's 3/4. So you have to kind of think about what that fraction might be and what you may have to multiply by so that you end up with whole numbers and not this sort of fraction of a number. So once we've got the empirical formula, we need to find the molar mass of that, which you'll see me abbreviate M, the cursive capital M with a subscript capital E, okay? And for this one, 12.01 for carbon times 2 plus 1.01 for hydrogen times 5, we get 29.07. So that's the molar mass of the empirical formula is 29.07 grams per mole. Okay, and we got one final step. All right, and that's going to be compare the mass of the empirical formula with the molar mass of the molecular formula. Well, all I'm going to do there is just take the number given to me in the problem, 58.14, okay, since it says that's what it actually weighs, and I'm going to divide it by the molar mass of the empirical formula. Okay, and you might see me abbreviate this molar mass of molecular divided by molar mass of the empirical, okay? And that's going to give you some ratio. All of your units are going to cancel out, and you should get some really nice convenient ratio. If you didn't, chances are you probably messed up your empirical formula somewhere. If you don't get a nice number here that's close to a whole number, then this is probably wrong. But 58.14 divided by 29.07 is 2. So what's that going to mean? Well, basically that means your molecular formula is 2 times that of your empirical formula. So my empirical formula for this was C2H5, and then I found out my molecular formula is double that. It's going to be C4H10. Okay, and that's the molecular formula for butane. And that's how you find it. So really the only extra step now is comparing the molar mass of the empirical formula with that of the molecular formula. And the molecular formula one is given to you in the problem. So here's another example. Stearic acid is saturated fatty acid containing carbon, hydrogen, and oxygen. So this time it's got 3. It gives us the molar mass as 284.54. It's composed of 76.0% carbon, 12.8% hydrogen, and 11.2% oxygen. What's the molecular formula of stearic acid? So solution is exactly the same as before, right? Begin by finding the empirical formula. So do all those steps, and then lastly, the new step, compare the molar mass of the empirical formula to the molecular formula, and that's given to us right here, 284.54. So let's look at the math here. 76.0 divided by 12.01, 6.33, 12.8 divided by 1.01 is 12.7, 11.2 divided by 16.00 is 0.700, so we're going to divide everything by 0.700. And we do that, we get 9.04 moles of carbon, 18.1 moles of hydrogen, and 1 mole of oxygen. So it looks like our formula for this is C9H18O, okay? And then if we look to add up everything for the molar mass on this, all right, and this is actually the way we can tell whether this is going to be right or not, is because if it doesn't go conveniently into the molecular formulas molar mass, then this is probably not right. So I've got 12.01 times 9, 1.01 times 18, and 16.00 times 1. I get 142.27 grams per mole. So that's my molar mass of my empirical formula, and I'm going to compare that to the molecular. Well, the molecular is given to us here, 284.54 divided by 142.27. I get a very nice number here, 2.00. Okay, if that wasn't a whole number, then this means I probably did something wrong somewhere. So, in any case, therefore, the molecular is going to be double that of the empirical. So, if my empirical formula was C9H18O, my molecular is going to be double that, C18H36O2. And they're not always going to be 2. Both the examples here were 2. Now you might get some that are 3, or if it's 1, so here's another example. If I have the molar mass of the molecular formula equal to that of the empirical formula, then they're the same. Okay, if that happens, then the empirical formula is the molecular. Okay, that can't happen. So if you get 1, if it's the same thing, if they're equal, then your empirical and molecular formulas are the same. That can happen as well. So don't let that trip you up. Okay, I'd like you to go ahead and try to do this last one. It says a compound contains 38.69% carbon by mass, 51.55% oxygen by mass, and 9.76% hydrogen by mass. If the compound's molecular weight is 93.12 grams per mole, what is the compound's molecular formula? So go ahead and try solving this one and see how you do.